Hi, this video is about Gibbs free energy. It's also just known as free energy. And this is going to finally be our decision maker if a reaction is spontaneous or not. Now, Gibbs free energy is defined as the energy that is available to do work. And like I said, the sign of delta G will determine if the reaction is going to be spontaneous or not. So, if delta G is negative, or less than 0. That means that the reaction is spontaneous in the forward direction that it is written. If delta G is positive or greater than 0, then the reaction is not spontaneous in the direction that it's written, but it would be spontaneous in the opposite direction. And finally, if delta G is 0, the system is at equilibrium, and we're going to talk about equilibrium in our next unit. So, the change in free energy of a system at a constant temperature is given by this equation. And so this again, these are deltas. So delta G, Gibbs free energy, is equal to delta H minus T delta S. Now, it looks like a pretty straightforward equation that's easy to use, but we've got to be careful of our units. Delta H's, if you remember, they were in kilojoules per mole. And the entropies, delta S's, were in joules per Kelvin mole. And so we've got to get these kilojoules and joules. We need them to be the same unit. So I normally like to work in kilojoules, but it really doesn't matter, just so the units match. And so what you have to do, let's just review. If you have kilojoules and you want to go to joules, so if you wanted to change your delta H into joules, you would multiply by 1,000. Or if you wanted to change your delta S into kilojoules, you would divide by 1,000. So going back and forth between these units should be pretty easy for you now. Now, this capital T is temperature, and it needs to be in Kelvin, and Kelvin is very easy to calculate. If you're given degrees Celsius, you just have to add to it 273.15, and you will get your temperature in Kelvin. And that equation is on your reference packet. So be very, very careful of your units. Make sure that the entropy and enthalpy units are the same, whether they're kilojoules or joules. I don't think it matters unless the question specifies, but they have to match. All right, well, I would like to build a chart for spontaneity. And so let me show you what we're going to do here. We want to know, is a reaction going to be spontaneous? I mean, that's a pretty important question. Some people call this the ghost equation. I guess if you put the delta S before the T, it spells the word ghost. All right, remember, if delta G is negative, it is spontaneous. So it's going to depend on the signs of delta H and of delta S. Temperature in Kelvin is always positive. All right, so here's what we're going to do. What we're going to do is we're going to say that we're going to assign different signs to delta H and to delta S. Okay, so let's say that our delta H is negative. So that's an exothermic reaction. And we said that that was a driving force, or that was thermodynamically favorable. Okay, and then T is always positive, and let's say that delta S is positive. And that's also favorable because remember, the second law of thermodynamics is that entropy in the universe is always increasing, so that would give us a positive delta S. So this is favorable and this is favorable. Will this reaction be spontaneous? And the answer is yes, because your sign of delta G is going to be negative. So that's the first case. Let's create another case. Let's say that delta H is positive. It's an endothermic reaction, not thermodynamically favorable, but it doesn't mean the reaction won't be spontaneous because it also depends on delta S. And let's pretend that delta S is negative. and that's not favorable either. So this is a positive number minus a negative is going to give us another positive number. This reaction will not be spontaneous in the direction that it is written. Delta G in this case it's always negative. Here it would have always been positive. And so that's why if it's delta G is negative, yes, it's spontaneous. Positive, no, it is not. Okay, we have two more cases to look at. Let's say that it is not favorable because it's endothermic, but it is favorable with our entropy. We're increasing in our disorder. Well, this reaction is spontaneous. Yes, no. It's going to depend on the temperature. At high temperatures, it will be spontaneous. At low temperatures, it won't. Okay, so delta G could be positive or it could be negative, and it's going to depend on the temperature. And when we say high temperatures, you might say, well, what's a high temperature? And what we would do to find out at what temperature does this become spontaneous, we would put delta G equal to 0. We would put in our values of delta H and delta S and solve for T to find out at what temperature would this become spontaneous. But it's ultimately going to depend on the temperature. All right, now our last case is where it's exothermic. That's favorable. And the entropy is negative, so that's not favorable. Will this be spontaneous? Well, maybe, maybe not. And it will be spontaneous if you're at a low temperature. But as you increase the temperature, as this gets bigger, it's going to become more positive. If that quantity gets bigger than this delta H, then it will not be spontaneous. So delta G could be positive or it could be negative, and it's going to depend on the temperature. So this is a chart that I don't want you to memorize, but you should be able to figure it out. Remember, a negative delta H is favorable, a positive delta S is favorable, and we want a negative delta G for a reaction to be spontaneous. Okay, we can also calculate free energies another way. There are things called free energies of formation. Just like we had enthalpies of formation and standard entropies, there are, yes, you guessed it, free energies of formation. And we could just look it up in a textbook, in an appendix. There are tables everywhere. And the equation to calculate the delta G of a reaction is the following. It's going to look familiar. It's the sum of the free energies of formation of the reactants minus the sum of the free energy of formation of the products. Did I forget anything in that equation? Don't forget the coefficients from your balanced equation. So just the same way that we calculated enthalpies of reaction and the exact same way that we calculated entropies of reaction, we can calculate the free energy of a reaction using the same equation except putting in our free energies of formation that would have to be given to you. And then remember, if your delta G is negative, you can say with confidence, this reaction is spontaneous. All right, well, we're going to practice a lot of these equations in class. So if you're a person who likes to do calculations, this will be the unit for you. Bye.